Actually, I will today discuss this a little bit, but as I signed the speaker agreement, I happily speak only about science and standardization. This is a splendid opportunity for me to do so. So actually, my presentation is still a little bit about my background. So I never could get rid of arts and music. I never could get rid of science. And this is what it was all in the end. Actually, a new technology or several key technologies, and at the same time also active engagement in standardization. So what am I going to talk about? I'm going to talk first about science. And actually, one of the most interesting discoveries was that inverse problems also work in audio coding, which so far no one would expect. The second thing is even more exciting, and in this I rely on the inspiration of Rudolf E. Kalman, that actually algebraic invariants, a quite interesting field, which is mainly concerned with coefficient functions, is actually also working in the realm of signaling and, of course, audio coding. And these two aspects, we have been so fortunate to be introduced to an own ECMA activity, which is now task group 22. And there actually, we focus on these inverse coding technologies. So I have some word on the standardization activities, and I also can give you the first glimpse on what is going to be the first future output of TG22, which is the base S5 coding document. To come back actually to inverse problems, the father of inverse problems was a Russian-Armenian physicist who already when studying discovered that actually it might be interesting with regard to atomic structure to study the quite similar behavior of eigenvalues and of discrete energy levels. And in a more mature state of his studies, actually he was finding a quite interesting nonlinear approximation for a rather complicated problem. And in these times, he simply named it, and this was in 1929, inverse problem. And this actually was forgotten very quickly. And as with the Kalman filters, only was picked up in the 50s. Today, there are 4 scientific journals on inverse problems. Whenever you have a tomography, you don't know that even this theory is working behind. The same is valid, of course, for measurement techniques and other applications. But in audio, everybody thought it would not be possible for one simple reason, because audio is not only considered with simply measurement, it's also considered with psychoacoustics. Interestingly enough, a dear friend of mine, Günther Theile, he published in 1980 a document, which actually was his dissertation. And there he stated that only by means of time and level, you could explain localization. And interestingly, we will come back to this issue in one moment. Behind lies an inverse problem, which directly refers not only to our ears, it also refers to our brain. Generally, an inverse problem always occurs when you have some measurement data and you want to know something in a precise area where actually you have no precise information. And there was actually one person, which is probably in electroacoustics the most eminent person in the second half of the 20th century, which was Michael Gerson, who worked exactly on this inverse problem in the 90s. And he was proposing an all-pass filter, which was a filter system which would be cascaded. And now, actually, you can even see the problem behind. Because if you have an all-pass filter, you don't only have time and level, but you also have frequency as a degree of freedom. And if you have frequency, all sound sources will be will be located either in the same spot or uniformly dispersed. And this is not a natural acoustic environment, because I expect that, for instance, two people which have the same pitch in their voice are located here and here, but either they are uniformly dispersed or they are placed in one spot. It doesn't work at all. So I was focusing on this problem of degrees of freedom, and I knew I had to eliminate frequency, which actually, according to Günther Theile, is possible. And what looks rather complicated here is actually an inverse model, a problem model, which allows you, by means of not only level, which is with regard to MS signals, which are only based on level differences, actually is not only working in the level domain, but also in the time domain. And interestingly enough, you get sound source separation, and even you get localization, even at the same frequency. So this, for the first time, we had actually a static filter instead of an adaptive filter, which adaptive filters are currently used in audio coding in the world of audio, which actually was very amazing, even to me, when actually I listened to the first results. What you find behind of this inverse problem model, you see actually that P it marks actually a level correction, and L actually simply means a delay. And if you closely look at those two formulas, you see there is an interdependency. So what you have actually is a discriminant relationship. And as I could prove, and as also you can see in practice, sound source separation in inverse problem modeling essentially depends on this simple discriminant relationship. So the first thing is, you can work in real time. The other thing is, it doesn't cost you any computational power at all. So this is something for mobile devices. So what you see here is right now the circuit of such an inverse problem solution. And it's simply, you see some interdependency. So actually you have some, these gains, they interfere, and there you have one additional gain you need simply for controlling correlation. But what it ends all up is a very, very, very simple algorithm. But there is one deep trouble behind, because actually as we depart from one single input signal, you of course have both the same information if you split the whole system up only in two channels, in both channels. And redundancy in spatial audio means a lot. It means actually, first of all, you have a room. And second of all, if you are in the anechoic chamber where there's no redundancy available, this codec fails. The great news is actually there is no recording made in the anechoic chamber. So we are very, very happy with that. And interestingly enough, with multi-channel coding, there is a solution for this redundancy problem. And this simply means the more channels we have, the lower the bit rates they are, the more performing is the system, which is not valid for parametric coding. It simply suffocates. And if you look at the spectral behavior, and this is actually the left signal of a normal stereo signal, which has been inversely coded, and this is now the left channel, and you now actually make the difference with the original left channel, you should, in the ideal case, get a dark screen. And it's really dark, with one little exception in the low frequencies. But these low frequencies, actually we have a shift also up regarding the scale. These low frequencies are not critical for localization. So by this little trick, we get all in one. This is actually for inverse coding. And there is a second very, very interesting thing. Let me say that, to my knowledge, Hilbert's work on über die vollen Invariantensysteme never was published in English. And everybody knows Hilbert transforms, everybody knows Hilbert space. But what about these invariants? He was making his dissertation on that, and this is his main work he ever did, and nobody takes care of it. And for some reason, as engineering is very linear, in the normal case, nobody cared that probably these invariants could be important. So what actually Hilbert was publishing in 1893 was an important discovery which simply said that these invariants, which are coefficient functions of so-called Grundformensystem, which is a very, very elaborate functional system, that these coefficient functions form a field. That's great news for mathematicians, but that's not great news for engineering. But actually, we were considered that actually this inverse problem model had to be calibrated, and as it's based on information of lower order, then of course we cannot, in any case, calibrate the system in a linear way. We have to do the whole thing with quite a lot of computational effort. And this would never work if you wouldn't use invariants. So I was actually consulting Professor Kalman on this, and he simply said, oh, there is a 100-year-old problem in mathematics. Isolate algebraic invariants with Gaussian processes. No one ever did it. He told me. He didn't tell me the solution. But actually, at least, I knew that probably there was something out I could look for. And it took me about 1 month to crack this problem. But indeed, as Professor Kalman said, this discovery that these invariants form a field simply means it's a hunting license. They have to be out there in Gaussian processes. And indeed, when I focused on apolarity, which simply means that all invariants vanish, they are equal to 0. And by using apolarity and by using projections on algebraic cones, I could actually solve the problem. So here you have the first algebraic cone, which is actually quite familiar to you. And there is a second one, which is also apolar. And now it becomes very, very tough because the third one is seems no more to be there. But of course, a plane can be looked upon as a very specific algebraic cone. And now actually, if you form, due to apolarity, you may be allowed to form linear combinations, you have, all of a sudden, you can make linear combinations of these three cones. And in the end, actually, you discover that the invariants lie exactly on this plane here. And this simply means that if you, for instance, have a signal on the oscilloscope, this is an ordinary stereo signal, then actually the invariants lie exactly on this diagonal. And what actually you also can do, you can rotate the diagonal by simply rotating the referential system. And by doing so, all of a sudden you have objects, and this is a typical, I would say, approach in the same field as Kalman did earlier. You're in the algebraic realm. You don't care about probability. And actually, we all in audio coding care about probability. And this gives us a lot of trouble. And by doing so, actually, you can formulate encoding algorithms which are very, very fast. So based on this idea, actually, there was TG22 being formed. And it's actually a big pleasure that we have right now at ECMA an audio group which never existed before. And this group actually has a liaison with MPEG. It also has a liaison where we also are active, by the way, and also with AES, which are concerning binaural standardization. And by doing so, we believe actually that the whole IT world is in need of really genuine 3D audio content. And evidently, this is the case, as is showing the Japanese situation. So we have named this system S5, Scalable Sparse Spatial Sound System. It's simply, instead of transmitting an adaptive filter parameter data, you're simply transmitting static data, which means that, for instance, for NHK 22.2, you can compress the whole spatial information for the same content down to 200 bits. And that's a lot. And by doing so, actually, you are simply addressing a spatial model inside the decoder who takes a parameter and actually makes happen a reconstitution of this 3D signal. So all these issues you find here are based on this very simple fact. So it actually leads to very high compression. It leads to reduced computational complexity because simply we're based on gains and delays. And we are actually, at the same time, we also have low latency processing because implementing a gain and delay, you simply have to feed it in the right way. It's not very, very difficult. And this is actually a scheme which is out of the current standardization document. So what you see here are the initial slides for the project, but already updated. So you see a whole system which you're all familiar with, but there are two elements which are new. The first one is the base S5 encoder, which is simply driving the spatial model. And the second thing is, of course, then you have a downmix, and then you have the inverse coding parameter data, which is simply goes down to this to these bit rates I've been talking about before. So if you only would express the whole system by mere means gains and delays, you would end up at 200 bit for NHK 22.2. And this means that this system is already functional at 48 kilobits per second, which is very low. The whole system works together with a base audio encoder and a decoder, which simply means you could use any codec. It could be a psychoacoustic codec, a lossy codec, or a lossless codec. And if you look right here on the decoder side, it's simply you find the spatial model inside S5 upmix. But actually, what is also happening by means of the configuration data, you can set up the decoder. For instance, in South Korea, we have a different format, which is 22.2. In Europe, we currently have the Aura formats, which is between 9.1 and actually 13.1. So this is a 3D, currently is a whole mess. But you can still address it with the same codec simply by means of the configuration data. So it's a very versatile thing. And the essential principle is simply you downmix, you transmit the inverse coding parameter data, you upmix, and inside the encoder, actually these algebraic invariants help the encoder to work really in real time because we only look at specific states at a given time ti. And which simply also means that you have the possibility, when you use a base audio codec, like for instance AAC or USAC, you use actually an encapsulation, which means inside AAC and also USAC, there are functionalities like, for instance, with USAC, the DSE element, which means you can transmit everything. So an existing 2D codec, and this is the mandate which has given to the group by the General Assembly, you can extend a 2D codec, an existing 2D codec, to provide a full 3D experience. And it's at the same time also, the data flows are compatible. So if there is no possibility to read S5, you still can read, for instance, in AAC, the files, which simply means in the end that you have a system which comes for free at no cost. AAC currently is functional in 6 billion devices, and there is no actually 3D experience ahead in the consumer world. We envision 3 scenarios, and there is actually another technology which allows us to really achieve high transparency, which means for internet broadcasting, you have high quality scenarios, which means with regard to communication, you have low latency scenarios, and still you have full 3D available. And you have also low power scenarios because the algorithms are not really they are really lightweight. So this is actually for the standard. And as you see here, this is actually a 3D setup. You have 24 loudspeakers. And this seems to be science fiction. You simply tell me, I mean, that's nice having such a standard, but who cares for 24 loudspeakers? No one will set up this. But of course, you can make a virtualization by means of head-related transfer functions, which simply means if you see me on stage and you listen and you see I'm talking here, it's simply because your head is working as a filter and is giving a quite awkward frequency shape to what actually is you would normally receive at a microphone. And these frequencies by our brain, and this is also concluding a little bit my scientific introduction, our brain is able to filter this out, to have the full sound, and all these bad frequency responses are transferred to localization. And so we can actually virtualize this on headphones, and at the same time, we can also do the same thing with soundbars. So forget about this. It's fully functional at lowest bit rates with consumer devices. Actually, I already gave a little report how the standard is like, and the most important message is probably it's working with the coding points of MPEG, and you can introduce additional loudspeaker configurations. It's a very versatile thing. It works with mobile devices. So this is for XMS 5. We have actually future activities, which will be standards on AAC and USAC, and we are, of course, happily looking forward to further active contribution from industry. So you're all welcome at TG22. Thank you very much.